In this video, we're going to go through types of cells and batteries, which is just going over the applications of both voltaic and electrolytic cells. And then we're going to go over cathodic protection, which essentially is just saying or going through methods of how we can prevent rust. So to start off with types of cells and batteries, the first one that we're going to talk about is a dry cell, which is just a sealed electric cell with semi-solid conductors. So below in this picture here we have a D cell or a D-size dry cell battery that's been cut in half just to show the anode, the cathode, as well as the electrolyte paste. So with this, notes on dry cells, we're just going to talk about it in general. You don't need to know the specific reactions that go on in a dry cell, but you do need to understand the general idea behind how these batteries are functioning. Okay, so these cells or dry cells contain an electrolyte paste inside of a zinc container. So the zinc container acts as the anode. And in the middle, there's a graphite cathode. So basically, the electrolyte paste is just a medium through which electrolytes can move through to get from the anode to the cathode. Okay, so moving on to more specific types of batteries, there's primary batteries, secondary batteries, and then there are fuel cells. So your primary batteries, those are going to be cells that cannot be recharged. So those are more like your traditional batteries. And essentially how this functions is that the outside functions as one electrode, and then the second electrode is embedded in the electrolyte paste. So pretty much just like what we've seen up here, just because D cells are one of those traditional batteries. And we're assuming that this is non-rechargeable here, and so that's why we would qualify it as a primary battery. Now with the second type of battery, that's just called a secondary battery. So this would be your rechargeable batteries here. So there's two kind of modes that these batteries run on. There's the discharge mode, so that's when you have the battery acting as a voltaic cell, so similar to a primary battery where we have a redox reaction going, a spontaneous redox reaction going, which produces electricity. Then the second mode is going to be the recharge mode, where you're running the battery as an electrolyte cell, where you're causing the reverse reaction to happen once you input electricity into the battery. So I'm just going to summarize this with mode 1 and mode 2, and we'll talk about, or we'll write out what I just said. Okay, so once again, mode number 1, that's the discharge mode, which is running the battery as a voltaic cell. So primary, this is similar to the primary battery where that's running as a voltaic cell. Right, so the reaction is the forward reaction is a spontaneous reaction. So RXN is just my shorthand for reaction. And then the second mode is the recharge mode, where you're running the battery as an electrolytic cell. So that means we're using electricity to drive the reverse reaction, which is non-spontaneous. So again, this RXN just stands for reaction. Okay, then last but not least, we have fuel cells. So that's a cell where the fuel is being continuously added. Okay, so your fuel essentially undergoes a redox reaction to produce electrical energy. So an example of this would be a hydrogen fuel cell car. So because a redox reaction is happening to produce electricity, essentially that means that these fuel cells are operating as a type of voltaic cell. So on the next page, we just have an example here. So methane is usually combined with oxygen to produce carbon dioxide and water vapor and heat energy. So they're giving us the reaction right here as a thermochemical equation here. How we know that is because the energy term is part of the chemical reaction. So usually the energy from this reaction is used to warm houses or run machines. In a fuel cell designed to use this reaction, the energy is used to produce an electrical current. So the electrons flow from the reducing agent, which is methane, to the oxidizing agent, which is oxygen gas. Now another place where we're going to see fuel cells being used is with space programs, and they're using a reaction of hydrogen and oxygen to produce water. So what's happening here is that we have hydrogen coming in, and we have our carbon electrodes that are coated with a platinum powder, which is going to be used as a catalyst. So a catalyst helps to increase the rate of a reaction there. Okay, so we have hydrogen gas coming in, and what happens when it reaches this electrode here and it gets catalyzed with platinum here is hydrogen is going to get oxidized, and so this would mean that this electrode is an anode. Okay, so the reaction that would be happening here, if we go to our table, so that reaction would be this one right here. And so we're starting on the right hand side, and we're reading this from right to left. So we're starting off with hydrogen gas, and it gets oxidized to produce hydrogen ions and electrons. So I'm just going to write out this reaction here. So what happens to these hydrogen ions is they move across this wet acidified plastic membrane, and they're moving across to get to the cathode, because if you remember, cations move towards the cathode, anions are going to move towards the anode there. So while the hydrogen ions are moving across this membrane to get to the cathode, what's going to happen is these electrons produced by this oxidation reaction, they're going to move through this wire to produce a current. Okay, and once these electrons as well as hydrogen ions get to the cathode, another reactant being supplied at the cathode is going to be oxygen gas. And what's going to happen is oxygen gas is going to get reduced in order to produce water vapor. Okay, and then that water vapor is going to escape out of the steam vent there. Okay, so those are some applications of fuel cells for you. And then this next question is related to the fuel cell for the United States space program. So you can use what we've just talked about to help you go through these questions for question 152. Okay, but moving on to how we can use our knowledge from this redox unit to prevent rust, there's a few different ways that we can do that. Okay, now why we want to do that is because metals make really great building materials, but unfortunately they also make great reducing agents, right? So if we look at, our reducing agents, all of the bottom ones are all metals here. So that's why they're saying that metals make really good reducing agents. Okay. So they make really good reducing agents, and they can undergo a spontaneous reaction with water and oxygen from the air to form rust. So we need ways to protect metals so that buildings and structures don't rust. So the first way that we can protect metals that we're making buildings out of is by using paint. So what's happening here is when we paint metal, so for example, if you have a car and obviously it's painted, that paint on your car is going to protect the metal in the body of the car from rusting. Right? If you've ever noticed a scratch on the side of your car and it begins to rust, that's because it no longer has the protection of the paint to keep it from rusting. So painting metals protects it from oxidation, which is just a fancy word for rusting. Okay. Now another way that we can protect metals is through galvanizing them. So galvanizing is a specific process in which we coat some metal with zinc. And galvanizing is very specific that it uses zinc to protect whatever metal you're trying to protect. So how it works is that zinc becomes the new strongest reducing agent. So instead of the metal that you want to protect reacting to rust, zinc will react instead. So zinc becomes the new strongest reducing agent. So I'm just going to abbreviate that to SRA. And zinc will react instead of the metal you are trying to protect. Okay, and another reason why zinc is important to use is because zinc, not only is it a stronger reducing agent, but zinc is also more corrosion resistant, or it's more resistant to rusting, which is why it's a good choice. The third way in which we can prevent rust is through using sacrificial anodes. So what that is just a metal that you're using to protect a more valuable metal from rusting or corrosion. Okay, so how it works is the metal that you choose to be your sacrificial anode, so the metal that's going to rust instead of the metal that you're trying to protect, you need to choose a stronger reducing agent than the metal that you're trying to protect. So it has to be a stronger reducing agent than the metal you are trying to protect. So, for example, if you have an iron pipe that you're trying to protect, so if we look, we find iron solid right here. Then if we're trying to use a stronger reducing agent to act as a sacrificial anode, then we have to choose some other metal below iron. So we need to choose a stronger reducing agent, which we will find below iron, in order to act as our sacrificial anode. Okay, so just arbitrarily, right, we could choose magnesium to be the sacrificial anode for iron. So I'm just choosing that arbitrarily. You could have chosen zinc, chromium, aluminum, sodium, calcium, barium, potassium, or lithium. Okay, but arbitrarily, I'm just choosing magnesium here for this example. Okay, and the reason being is because it is a stronger reducing agent than iron is. So, for example, you have an iron pipe that you're trying to protect. So, we can pick a stronger reducing agent, such as magnesium, to act as the sacrificial anode. Okay, and then last but not least, you can apply a current to whatever metal you're trying to protect. So how it works is by using a direct current from a power source, your cathode gets the electrons from your power source instead of like your anode receiving the electrons from your power source, which means that it will prevent it from rusting.